Okay, everyone. Hi, and welcome to this webinar. I'm going to be talking about what makes RavenDB goes fast. And this is a really interesting discussion because there is quite a lot of things that went into making RavenDB fast. So let's hop right into that. So the first thing that we have to understand is that we spent a lot of time and effort and
Aaron, can you come
yes,
a little bit closer to microphone because I don't hear you well.
That's not a good thing. Let me try. Let's see.
Because the voice is on my side on maximum, but
Can you hear me now?
yeah, now it's good. Very good.
Oh, it's good? Okay, that's wonderful.
Yeah.
Okay, so as I was saying, we are here to talk about why RavenDB is fast, or how did you get to the point that RavenDB is fast. And the way that we did it is to spend an inordinate amount of time focusing on that. And that's the story. Spend a lot of time doing something, you get good at that. But you're not here to listen to me tell you that, oh, spend a lot of time on that. This is not the 10,000 hours to be an expert or something like that. Instead, I want to give you some details about how we got them. And in the end, I'm also going to touch on some of the things that you can do inside of your own system that will make things better. So let me give you some history. In 2009, I started working on RavenDB. That was after I spent a couple of years literally dreaming about it. I would wake up at 2 a.m. and have the architecture diagram on the ceiling. That was quite annoying, I have to tell you. In 2010, we released it to production and people actually start using that to store real data. And that was wonderful, it was scary. And we started to get more and more users and more scenarios. And we realized that we were stuck, and we were stuck hard. And why is that? Because the architecture that we had was not sustainable. We couldn't push it forward. I mean, we could push it forward. The problem was that the scenarios that we were trying to build, the things that we were trying to make, did not make sense. It wasn't able to, we weren't able to, okay, I can optimize that by 5% here, 10% here, but our users wanted to be able to run 100 times faster. So we had to basically go back to the drawing board, and we re-architected the whole of RavenDB from the ground up. And the way that we did that is that we took the 6 or 7 years of experience that we had in building RavenDB, and we sat down and we thought about how we're actually going to be able to do that. And what we actually did was, okay, instead of trying to join together several disparate pieces, let's go and build something that is designed from the ground up in a cohesive manner. So the way that I'm accepting data from the network is going to play well with how I'm writing data to the disk, which turns out to be a really important scenario from our perspective. And let's take it forward. So when we talk about performance, we talk about how you do that. There are 3 things that you have to pay attention to. First of all is your overall architecture. A great example of that, if you're using a distributed architecture and you need to call to 3 different services to do an operation, you are always going to be slow. There is no amount of optimization that will help you because you introduce 3 separate latency sources into your system. So that's one side of things. The other side of things seems obvious, but it's actually quite interesting. This is what sort of algorithms and approaches do you use? And finally, it gets to the point where, okay, I have the right architecture. I have the right algorithm. Now I have to be able to take that and translate that into the most efficient code possible. And I want to give you a great example in this regard. Sorting. There is a proof that quick sort is supposed to be the fastest sort around. But it turns out that while from a mathematical perspective, that may be true, team sort is actually faster. Why is that? Because math and the real world don't necessarily play together, because math, in this case, ignores certain realities. And for smaller sections, you might want to use some other algorithm, because it is better in terms of the memory cache hierarchy, for example. So now we have the most common and sorting algorithm is actually something called team sort, which is basically a bunch of if statements. If the size is larger than X, use this. If the size is smaller than Y, use that. And that's about it. And it turns out that in practice, it has really great performance. So there is a lot of stuff like that, but I will touch on that in a bit. Let's start from the overall architecture and discuss how it works. So the fourth thing that I want to discuss is JSON. RavenDB is a document database. It does JSON for a living, a lot. And when we started out, we used in terms of JSON as the library that we wanted to use. And it is a great library. It's really functional. It has lots of features. It does a great job in being a JSON library. It is also not meant for high-performance systems. And I want to give you a really simple example. Let's take into account that I have this JSON document. And let's say that we do it like this. Great. So now I have this JSON document. And as you can assume, I have a lot of items here, so it's big. I want to be able to access this one. What's the cost of doing that? If I'm using JSON, I have to scan through all of these values. It's actually worse if I'm using users of JSON. I have to materialize the value. I have to create an object in memory that represents this entire document. And the more complex my document is going to be, the more expensive it's going to be. It's actually worse because now you have second order effects. Parsing cost is a cost, but then realize that, oh, I have a really complex document which created a really complex object graph, which now means that the GC has to do a whole bunch of additional work. That kind of sucks. So we needed to consider how we actually going to be able to optimize things. And we built our own JSON parser. This is not that surprising. A lot of people build JSON parsers. It's a really nice system. There is a problem. What's that problem? The problem here is that what we needed to do is to get to this. We wanted to be able to say, I want to get to O1 parsing cost. And the way that we do that is to say, okay, I'm a JSON database. I'm not going to be using JSON internally. At least I'm not going to use the JSON format. I'm going to be use an in-house structure. And this structure is going to be called splittable. What does it mean, splittable? It means that I can take it as is and do things to it. So here I have imagine that I have this data. And now I can do things like and what's the point in doing this? The whole idea is that the data is just a byte array. Actually, it's sitting on a memory map files. This is not actually a byte array. This is a byte pointer. And now I'm able to access any data in the document without having to go through the entire document. This required us to build a really complicated system just to represent the way that we build documents in memory. But it also means that in order to access a value of a document, I can do that ineffectively or one cost. For that matter, the way RavenDB does things is really quite interesting. Because what we are able to do, we're able to say something like this. Let's learn about the access patterns that you have in your system. And the more you provide me with the same access patterns, the more I'm actually able to optimize according to how you're doing that. And that sounds like it's enormously complicated thing. It's not. I want to show you something. In here, how does this work? Internally, there is a list of properties and positions. So I can say, when you give me the data, search for the data property. And this tells me that the value of the data property is in position 200. So I can just jump there. It says, give me the the item property, which is in 400. And then I can go to the array and says, give me the 20,000 element, and just to jump from there. But remember, this is the list of properties. I need to search on that. But I can do something better. So what I'm showing you right now, this is the RavenDB code. And we have the blittable JSON reader object. And we have this feature. So get property index. And now we're doing this. Now I want you to look at the code that we have here. This is a pretty trivial code. And what it actually does, it implements a binary search between the two of them. Now, this is interesting. Where is it? It's not here, it's in maybe here. No, it's here. And so this is a binary search. And I had something here that I wanted to show you. I can't remember where we put that. Because what we did, and it might not be here, it might be in a different location, we have the ability to remember what is the last value that you found and then start searching from there. So basically, this is supposed to do that. But I don't remember where we did this, which sucks. I'm sorry, I had this amazing demo to talk to you about, and now I can't actually show that. That's really sad. Okay. And probably I will probably see that in a couple of minutes. I remember, but for now, let's move on. The whole idea is that we are able to build our own JSON representation that matches what we actually need from the system, that has this O1 parsing cost. But remember that I spoke about this notion of cohesiveness. How does it play into that? Well, what you can see is that RavenDB is actually using, in terms of storage, you can see that what we are actually using is a memory map file. Memory file means that I can access it by pointer. And then I have no preparation cost. I don't have to parse that into a managed object, which means that in turn, I'm able to just utilize this directly. So these two features, memory map file and the bleedable format, suddenly have a much bigger impact because now I have a zero copy model. I don't need to read from the disk, parse, and then do something. I can search for the value, get the pointer and hand it directly off to the send it to the user routine at a greatly reduced cost. Now, here is another example. And this is where things get really interesting. RavenDB has this notion of indexes, which means that you have a better way of actually searching for data. But this has a downside. If a document is being modified, we now need to run the indexes. So the easiest example is in here. I'm going to search for someone by name. Here is Nancy. Now I'm going to go here, and instead of calling her Nancy, I'm going to call her Nance. What happens now? What does RavenDB need to do? Well, it needs to go and update the index because I don't have an Nancy anymore. I have a Nance. And for fun, let's call her a nonce, which is a terminology in cryptography. So think about what it means. I modify a document, and then I need to run the indexing to do that. What happens to the cost of doing that? Well, it means that every time that I need to modify a document, I also have to apply the indexing. And that leads to a really costly scenario where I always have to update the indexes and they are costly to do. So instead of doing that, we're not going to do the indexes. That doesn't make sense, right? If you're not doing the indexes, then your query is going to be wrong. So what am I actually going to do? Well, this sounds like a Zen statement. Go slow to go fast. What is it? Well, it turns out that indexing a single element at a time is really expensive. But the cost of indexing one element or 10 elements is roughly the same. Because the overhead of setting up the indexing run is so hard. So instead, what I'm going to do, I'm going to say, hey, you know what? I'm not going to be indexed right now. I'm going to set up a background process that would index when it sees fit. And it's going to capture as many documents as possible. Now, if you have a low latency system where you write in every now and then, like 3 times a second, that's really low. And there's a lot of time. So I can spend the CPU cycles and the overhead to index each document independently, because obviously I still want to index them as soon as possible. But what happens if you start putting more load into the system? What happens if you're writing 10,000 documents per second, 100,000 documents per second? What's going to happen then? You know what? Let's see. And here we go. Here we have RavenDB. It's running. And let's go here and look at the local system. Library 2. What I'm going to do, I'm going to go here and define an index. Well, I'm not going to define index this way because I broke it. Here is the index. Do not do this. Do not do this at home. It's more fun to do it this way. Okay. Now I'm going to go ahead and define an index. My index. And here is an index. It's a pretty simple one. Nothing really to write home about. But let's make the text field into a full text search. So now we have an index. You know what? I will even go further and say, let's make this into a coax index, because that's more fun. So now we have a coax index. And it's not really that interesting because we have no documents. So let's go here. And let's import this document. So what I'm going to be doing now, I'm going to be import data, and you can see that I'm importing the data at a relatively fast rate of tens of thousands, and it's going to reach 100,000 in a bit. And also nice numbers. Oh, I know why it's, so let me show you. No, we let it run, and then I'll show you something fun. Let's go back here. And now, in a few seconds, you're going to see some details here about the rate of indexing. And I'm pretty sure user books, so that's fine. Why aren't you indexing? Oh, because this is users. Sorry, I have the wrong. Currently, I'm importing the wrong data. Let's do this. So I have a really nice demo that I want to show you. So that's it. So here we have this are the documents. And I'm just going to reset this index. Now we'll be able to see what's going on. Now we have a need of actually indexing 50 million documents. What I wanted to do previously, I want to show you how it works when we are inserting and indexing at the same time. I will find where that document is residing in a bit, and then I will be able to do that. Second. In the meantime, look at what we have here. We are indexing the data. But at what rate? So if we're indexing each and every document independently, this would be far, far slower. But because we are indexing in batches, you can see how this works. So here we index 622,000 documents. And here's another, takes 18 seconds, but notice that some of the cost here is the per map cost, so the per document. But here is 2 seconds and 1 second of just the write the data to disk portion. And we may have larger data sets still. So I'm going to stop it for now, because I want to also be able to do the demo properly. Let's go back here. So it turns out that being slow actually means that we're going faster. We are letting us gather more work before we are starting indexing immediately. Now, so this is a really interesting concept, and it is a core concept for RavenDB. Why is that? Because if you're working in a distributed systems, you might have heard the notion of the fallacies of distributed systems, where we have where we have the notion of latency is zero, bandwidth is infinite, and people who make those sort of assumptions are going to end up in a really bad place down the line. And why is that? Because of the way that they are actually designing the system doesn't match the reality of how it works. And then you realize that if you talk about a single system, a server, it is also a distributed system. Look at the disk. This has latency. This is the average response, and this is an NVMe drive. It's not the best NVMe drive, but it is an NVMe drive that you have to use. What's the impact of this? That writing or reading from this takes me 10th of a millisecond. Well, it means that I'm going to be sitting there waiting at the CPU level. So that sucks. If I'm looking at the memory, you can see that I have this memory, and there are typically more information here about that. I don't know where that went, but you typically have details about the L1. Oh, it's here. Sorry. Here we go. So now you can see that you have the memory, and then we have the caches, L3, L2, L1. What's the meaning of this? Well, L1 is really, really fast. L3 and L3 is slightly slow, but still faster. And then you have the ability to think, oh, wow, if I'm using this concept, what does it mean? It means that I can think, oh, I'm going to memory. That's super expensive. If I want to make a sandwich and I go to the store and buy one slice of bread, go back home, and then realize that I need to go back to get the second slice of bread, I'm going to remain hungry because I'm only walking back and forth to the store. Nothing else. This is utterly ridiculous. So everything in RavenDB has this concept of a batch. We are processing indexing as batches, or even processing transaction in batches. This turns out to actually be a really interesting property. What happens if I have two concurrent transactions that want to modify some documents? RavenDB is an ACID document store. It is transactional, means that I have to hit the disk in order to operate properly. I just told you that disk is slow, right? Really slow. Now, this is actually when we're not doing much. Let's go back here and resume the indexing. Pay attention, you see something really interesting. So now, what is the process that we have here? I'm starting to read from the disk. In a few seconds, I'm going to be starting to write the index data to the disk. And this is going, this now at spiking up. Now we can start seeing some numbers because now we start gathering some activity. Now, this is the local NVMe drive that I'm using. Try to imagine what happens if I'm running on a cloud instance, or God forbid, a hard instance. And even so, you just saw it spike to 20 milliseconds. This is a really slow response rate. So I have to assume that I have to take it into account in the system design. And batching is one of the ways that I'm doing that. So here is a typical example of how this works. If I'm working with RavenDB and I'm looking at the data, and it doesn't seem, okay, I have to do some work, and then I have batching. Okay, what does it mean? Well, let's take the example of a bulk instant. and what it means. Here's what we start. We have a whole bunch of documents that we want to put into the database as soon as possible. And it turns out that this is actually a super, super complicated story. Why? Here's why. I'm running on a cloud instance. I'm starting to insert 10 million records. What's going to happen now? Well, it's very simple. It's very, very simple. I'm going to get some data, write to this, get some data, write to this, and no one is happy. But I'm running in the cloud. What does it matter? Well, if you're running in the cloud, one of the things that you can do is run on a burstable disk, which means that you move from being able to write 100 megabytes per second for, let's say, 10 minutes, to being able to write 1 megabyte per second. And try to imagine what it means. I'm the writer. I'm the one that generates the data for the bulk insert. And I know that I'm going to be able to write to you at a rate of 100 megabytes per second. So I'm doing that. And all of a sudden, at the back end, we flip a switch. And we went from being able to write 100 megabytes per second at this level to being able to store just 1 megabyte. And at the same time, I'm the one who is writing to you on over TCP, and I'm used to sending you a lot of data, so I'm streaming that as soon as possible. But when you get stuck at a 1 megabyte per second a disk, things start to queue up and queue up and queue up. In the 1 second it took you to realize that this is the case, I sent you 100 megabytes. This is now going to take you 100 seconds to spill to the disk. From my perspective, I keep sending you data and you never told me that you got it. So this is a scenario where the TCP implementation, the way the TCP works, actually has an impact on how you design your system. Now, another thing to remember is that actually writing the documents to disk is not just, okay, let's write them to a file. We have to parse them because you send JSON over the wire, and we have to translate that into deletable format. And then we have to figure out where on the disk to put them. We have to update the storage indexes that we have and a bunch of other stuff like that. That's kind of sucks. But then we have to write it to the actual disk, which is super slow and can have huge variance. So actually for bulk insert, we have 3 separate actors that are playing with us. The first actor is going to be reading from the network, paying the cost of parsing the data, which means that I read a bunch of documents, a bunch of bytes from the network. And while you're sending me the data, I'm going to be parsing that. And then I'm going to pass that to another actor to actually write it to figure out where to write it, update the indexes, everything that needs to be done. And that actor is then going to hand it to the disk to actually write it in the right location. But that just makes things more complicated, right? Well, the secret here is that this one is going to do its job. This one is going to do its job. And then it's going to hand the package to this one and continue reading from the network. And this one does its job and give a package to the next one, and then here. So we actually have several parallel behaviors all at the same time. But remember, I actually have to be worried about being too fast, of reading so quickly from the network that if I have a hang up later on, you wouldn't be able to recognize that and slow down the sending process, the sending rate, before you realize that. So in order to handle that, I actually have two parallel processes each time on each one of these actors. So first, you read from the network, and then you send it to the next one, and you keep going from the reading from the network until we tell you you're done. And same thing in here as well. So the whole idea is that eventually this balances out to roughly the speed this is able to gather. But we have enough leeway to adjust dynamically. This is actually a case where we're trying to not be as fast as possible, which is, it's a surprising feature to say. I don't want to be as fast as I can be, because I have to be worried about effectively someone throttling me down at the other side. Now, so we spoke a little bit about architecture, and I gave you some of the details around that. Let's talk a little bit about algorithms. And most of the algorithms that we use are really old. We didn't need to invent any new algorithms, and for the most part, we use what works. We actually have quite a lot of research and application of modern practices. For example, coax, our indexing engine that we released recently, have a bunch of things that are really new, as in a couple of years old in terms of published algorithms. But for the most part, we are generally doing old boring things. Old boring things is great because it means there is a lot of research and aspects around that. So let's talk about what this means. For example, B-tree is, I think the first mention for B-tree is from the 1970s. And the paper is called Ubiquitous B-tree. So even in the 70s, everyone used that. I want to give you a hotspot that we run into. And you can see it here. This is a course benchmark that I'm running. And you can see that 10% of the indexing rate in this particular scenario are spent inside of this guy. So this is a method that you're probably not familiar with. It's a way to do slightly more efficient operations on a dictionary. Doesn't really matter that much. What really matters is that we are spending 10% of our time inside of a dictionary. And this is actually quite common, because a dictionary is one of the first things that you reach out to in order to improve performance. So this is actually something that we have a lot of experience in, trying to figure out how you can optimize those things. And what it turns out to happen is that in many cases, what we are looking at is not trying to find the appropriate algorithms, but to find what we can avoid doing or avoid doing right now. A great example is the fact that you typically have the ability to trade space for time. What does it mean? For example, I may be able to compute a value down the line, but it may actually be cheaper for me to do that, to pay the additional storage cost and store that directly. And this is a common trade-off. And there's nothing fancy in here. That's the title of the slide, but I wanted to emphasize that we're not doing anything special. We're just here, the right algorithms, because the one thing that you will find out when you profile is that, oh, I call this in an n square manner, and someone just shoot me now because how could I be so silly? Okay. Another thing, let's see something. Let's stop this. Now let's look here. I want you to look at what I'm doing now. I'm importing a document. So this is the library system. And you can see that I'm doing that at this particular rate. Okay, that's nice and all. We hit the 100,000. I'm happy. Now I'm going to do the same thing, but I'm going to do something slightly different. I do not want to wait until this is over. Let's go and kill this thing. Library 2. Now I'm going to make things slow. So what did you just say? I said I want you to compress the documents. Let's see what the impact of that is going to be. Remember that we reached about 100,000 writes per second quite shortly after we did that. And we had a spike of about 140,000 documents. And now we're at this rate. And it's going to slightly climb. And after a short while, we're actually going to be, this is going to take about 2 to 3 minutes, if I remember properly. But even so, 80,000 per second seems fine. And let's wait until this is at, let's say, 3 million. So where was that? What? I'm confused. One second, let's abort that. Thoroughly. So it doesn't like it that much when I'm doing this. Okay, so we have 3.2 million documents. It takes 1.96 gigabytes. Library 3. Now without the compression, and again, this is better, right? This is much better. But let's see here. See these numbers? We're starting to stress even the NVMe drive. And we're going to let it to 1 until it gets to about 3 million. And about. Yeah. The file size is about, the file that I'm importing is about 1.8, sorry, 108 gigabytes. Takes a while. Now I want you to look into this. Roughly the same number of documents. This is 50% smaller. And this is where we start getting into interesting details. On this particular machine, I have no I/O constraint. But what happens if I did have the I/O constraint? If I'm running in the cloud on a GP2, IO1, those sort of disks, it would mean that reducing the size of the reads from the disk actually has an impact. 4 kilobyte is about 1 IOP in most cloud platforms. And you're paying for IOPS. So if you want to read, so not 4 kilobyte, 256 kilobyte is the 1 IOP. So if you need to read 50 documents, each one of them is 10 kilobyte each, then that's 2 IOPS just to read them from the disk, excluding everything else. If you compress them, they are half. Well, that means that you get twice the IOPS. And it turns out that we are actually far more limited in I/O than disk, in I/O than CPU in most cases. So actually spending more CPU time means that we're doing better. Okay, let's look at some of the low-level things that we have to do. I write code in C#, and then I want to look at the JIT and see what it's doing. I have a lecture that talks about using C# as a system language, because this is what we use to build RavenDB, obviously. And you can see some of the things that we are doing. In this case, this is using a vector intrinsics to be doing operation. In this case, this is on 8 items at a time, which translates to roughly 8 times fast. And I want to show you this guy. And I want to show you this in particular. So we are now working on an improved sorting algorithm. And I just got to show you the code. Where is it? It's not here. It's not here. Second. It's here. Behold the beauty. This is obviously, by the way, machine generated. But the whole idea is that we're able to generate a whole bunch of super optimized code to do this sort of sorting. And this is the sort of code that you never ever want to read. I actually have a PR that has about 200,000 of lines like this. But the whole point about doing that is that we're able to utilize it at a very low level to understand what's going on. And now let's talk about what you can do in your code to make things faster. I don't expect that you would go to the length that we are going to in terms of achieving performance. And for the most part, I don't think that you need to. So here are some of the most important features. Let's go here and talk about them. RavenDB allows you to issue a query. Here's a query. Now I want to be able to get here is nonce, and who does she reports to? I have to do another query in order to do that. Or I can do this. Now in one shot to the server, I get Andrew, employee number 2, who nonce reports to. This feature is called include. And the basic idea is that instead of going to the server multiple times, you tell the server, hey, I already know that I'm going to be needing this related document. Give me right now. And in the same sense that going to the store to get one slice of bread and then going back to the store to get the next one is a really bad way of making a sandwich. This is the same thing. You reduce the cost that you have significantly by reducing the overall latency that you have. Another aspect is here, lazy operations. And what's the idea here? The idea is very simple. You have the ability to execute query in a lazy fashion. Those two do not generate a query to the database. Instead, they are stored in the session until you access them. And then RavenDB is going to send multiple independent queries to the other side. And again, what's the point? Well, the point is very simple. Don't talk to the server too much. Go once in the same way and go using the same grocery example. If I'm going to grocery store, I'm going to take a list. And on my refrigerator, I have a notebook that says stuff to buy at the grocery store. And every time I need something, I put it there. And that makes sense. This is how people work. And you can make your software do that as well. And that has a huge impact on performance. The nice thing about this, if you use this sort of method, then you naturally have several explicit steps in your architecture. First, you state upfront, here are the details that I want from the system, from the database. And then you get those details, and then you process them, and then you're done. It's very simple and easy. One query to the database. Another aspect here is that if I'm using this include here, I'm getting the full document back. In this case, this is a really small document. I'm okay with it. What happened if it was larger? Then I'm running into an issue that I only want to display the first and last name. So instead of getting whole documents back, I can do this. And here is nonce. I reduce the amount of data that I'm sending. I can also do this. And here are the two items. Now I'm able to just load just the data that I want, saving on network bandwidth. I can load related documents and reduce the amount of parsing complexity, everything that I need to do, especially going back to the server. RavenDB also has the notion of static indexes. And I want to mention them specifically because they have a feature that some people aren't actually using that much. Where is the, come on, let's go and create a new database. And now we'll be able to see the indexes that we have here. And one of those indexes is called all those totals. Would the real index show up? Here we go. And you can see that we have this computed value. And why does this matter? This matters because of the way that we operate. Static indexes and those sort of things mean that you don't need to compute during the query phase. You only compute during the indexing phase. What does that mean? Well, quite simply, it means that we don't really need to worry about it. Queries are fast. Indexes are running in the background. We can afford to move costs there. Same thing happens when you use automatic indexes. You generally don't need to think about it, but you run your queries, and RavenDB is going to ensure that things will be fast. You don't, oh, I forgot to have an index here, and that's going to kill my system. This is interesting. Lexicographically sortable IDs. What's the meaning? This relates to how RavenDB internally store the data. The more, if you use GUIDs for your data, then RavenDB has to place the data once here, once here, once here, once here, etc. This creates then something like this, a deeply nested structure. And you have to pay to traverse the whole thing at the same time. If you use lexicographically IDs, on the other hand, you can put them right next to each other, and all of them are going to be under the same umbrella. So this is actually going to have an impact. For the most part, you don't need to worry about it. The way that RavenDB generate document IDs for you by default means that they're going to be mostly already sorted for you. So that's cool. No need to worry about it. You can also do something like this, and RavenDB will use this format, which is obviously lexicographically sorted. There's a whole bunch of other things like that, but in general, I just want to call out against doing this, because then we actually need to generate a GUID, and that's not ideal. It's not the end of the world, but it's not ideal in terms of performance. Finally, I want to talk about caching. Take a look at this code. What happened if I would run it twice? Let's see. In order to show that, I'm going to show you how it looks from the perspective of the network. So we have this notion of a traffic watch. And I'm going to load, second, how much of crap. I want to see this. Okay. Now you can see here is the document in question, product 76A. Now I hit F5, and here is product 76A. But notice this versus this. What happened? Well, it's very simple. Under the cover, RavenDB is using HTTP and e-tags. So whenever you send a document, whenever you read a document from RavenDB, RavenDB tells you, here is the change vector, here is the e-tag for this particular document or this particular request. When you make the request again, the client will automatically tell the server, hey, I already got this particular version. Do you need to send me a new one? Or can I use the one in my cache? And the answer to that, in most cases, is that, oh, the document didn't change. So I still had to go to the server, but I didn't spend any bandwidth getting the document I already have back from the server. Another aspect is that we have the notion of aggressive caching. And with aggressive caching, I'm actually inverting this relationship. Instead of going to the server each time and asking, was it changed? Was it changed? Was it changed? I'm going the other way around. I'm going to the server and telling it, let me know when a document changes. And until that happens, I can serve result directly from my in-memory cache. Zero network traffic. Try to imagine what is the impact of that on your performance. It's huge. And you basically get that for free. You just need to know, oh, I need to enable that. And this, the reduction in this one, the reduction in network bandwidth because the document didn't change, you get it for free and you don't even need to enable something. Okay, so this is about time. And if you have any questions, we're very happy to answer any and all of them. Either on how you can make your application faster or how we build RavenDB to be faster in general.
Thank you very much, Oren, for the presentation. I have actually questions, but we are running out of time. I can send you if you want on the chat.
I'm not limited in time. We still have another few minutes.
Oh, okay.
I'm done with my topic, not with the webinar.
Yeah, sure. Well, when Christina contacted me, I didn't know about Raven DB, so a little bit research and checked on the DB engines, this comparison, because I'm currently working on one project, and I thought as a friend maybe to just propose this database. Currently, I'm working on architecture and implementation of some IoT platform, and so I see what is how compares MongoDB and Raven on this DB engines. You probably know that that page. So about the above, since I'm currently using the MongoDB for this, and yeah, I could introduce or present the RavenDB there to the company that they are aware of the product, and maybe, but for this current project which I'm currently doing, I am afraid it's a little bit too late because already implemented everything around, but yeah, why not to try? Questions about that. So for the current project, for example, time series are important. Do you support that feature?
I'm not ignoring you, I just want to show you. Here is a sample data. And let's go and look at employees. And we have time series right here. And you can see that here we have the heart rate over time. And we can plot that over time. Or you can see here the actual results in a tabular format. Here, the total counting average on an hourly basis. Let's do that on a 1 minute basis. Let's do that on a 1 hour basis. Now we can see I have those details. So RavenDB actually have built-in support for time series. We also have the ability to store, in addition to just the document JSON, we have the ability to store binary attachments. In this case, here is Steve. You have the ability to go here and look at old versions of the data and a whole bunch of other stuff like that.
Well, great. So about the querying, I saw you have some SQL-like querying language, but when we compare it to MongoDB, because I'm currently working with that, it's aggregation queries. How can be done? Is it supported, and how do you do that kind of things?
So here I have orders, and I want to group. You can see, let's say I have lines. I have ship to city. Select. And here you go. This just gave you the results that you want. Notice that when you compare it to Mongo, the amount of mental weight that you have to deal with is minuscule. You're used to understanding how something like that works. If you want to do something like that using MapReduce in Mongo, you typically have to either use the aggregation framework or to use to write actual MapReduce operations, and this is not something that you just spin out directly. Another interesting aspect is, let's see what happens if I'm doing something slightly more complex. So now I have lines. I want to know how many items, how many orders I have for each product. So I can do something like that. So this is an aggregation or a nested value inside of an array.
And for example, interval
Correct.
Aggregation on time series data, for example,
I think I've actually shown that, but it looks like this. So what you can see here is, let's go to the heart rate, go by 1 hour and give me the average.
It's, that's great. It's much simpler.
Or the sum or whatever you want. Yeah.
Great.
You can even take this further, just to give you some insight. In the sample data, we have companies, and company also have a time series. And the time series that we have here actually have multiple values per time frame. And this is the time series for company 88. I can define an index that operates over time series. And what it does, it aggregates per month, per country, the total volume that you have. And again, even if you have billions of entries in a time series, you're still going to expect to see this sort of query types.
Okay, thank you. The other thing which could be important for the current client is do you have something similar like Mongo Atlas, where I see that you have a simplified, or let's say opinionated, or I don't know how to call it, deployment on Microsoft Azure, because they're using currently Microsoft Azure. So how do you have something like Mongo Atlas where people can use it?
Cloud.ravenDB.net, and you go here, And give it a second. It needs to query quite a lot of data, but here you go.
Okay,
So
great.
find the location, find where you want, and you just have that and it works.
Excellent.
Yeah, zero complexity from your perspective.
About, let's say, deployment on premise or on Kubernetes, I see also you have that on the ATS.
Yes.
But I just now looked, I didn't go into details. Well, what do you have? Is it simple Helm charts? Is it Kubernetes operator or? Pardon, sorry.
Let's see.
Apologize. Installation of Kubernetes. Yes, it is exactly the link I'm looking at.
Yeah. And here is the Helm chart. Oh, come on.
It's not the link which I was looking
I don't know why I did that. Maybe it was RavenDB.
So Helm charts, just to answer.
Yeah, it's somewhere. I don't remember where we put it.
So it's not Kubernetes operator or stuff like that. Just
yeah, we have this. We absolutely have this. Let's see if I can find it quickly. Here we go.
yeah.
And here. No.
Yeah.
There was
Okay,
the
classic Helm charts.
Good. Let's this step.
I will have a look into it, and
I'm throwing that into the chat so you have easy
perfect.
access.
So this client is in utility area. Do you have some example use case in this field?
What do you mean?
Do you have some example or use case in utility field like electricity?
Yeah, true. I don't know if we have.
But you have a client in this area which is using RavenDB.
Let me check. Where is that? There is some. I think it's somewhere around here. There's some use cases. Here we go. And we have a bunch. I don't remember where it's located right now, but we have some around that area. Yeah.
Okay, great. Because I will ask very simple question because that question will be, I will be asked that question. Why we would use RavenDB when we have already MongoDB? What
peace of mind.
I ask?
Peace of mind. In general, I will give you the smallest example I can think of. I
have really willing, I'm like that CEO is presenting this and also some guys from Serbia are working for your company. I have willing to do it and present it and even do the kind of POC, and show it. But you will have.
Let me show you an example of mine. Okay.
Yeah.
Here I have a database that has about 3.2 million documents. I'm going, and it has a user documents that are not really that interesting documents. So I'm going to be doing something like this. It's going to run, and sucks. I have lots of data. And in about 15 seconds, it's going to give me a result. And that's okay. I'll get some result, and that will be fine. Now, the interesting thing is that it says I couldn't find it. And it is interesting why, because it's still processing. You can see the speed in which it is doing that. We let it run, complete. It's going to take a minute. And now I'm going to rerun the same query. And let's try a different one. Here is me. But notice what happened. What did I actually do? Here is the original one. I issue a query on a non-trivial amount of data. And the first time it took some time. And he told me, hey, you have to wait. The next time this happened, the query was instantaneous. I didn't have to spend 3 weeks optimize my application, trying to figure out all of my indexes and stuff like that. Another aspect that we have is that this applies effectively across the board. You can see this is the dashboard that you get with the community edition. So we externalize a lot of information for you specifically for this purpose. If I'm looking at the cloud instance, I wonder if I would have. Okay, there is not enough load on that instance, but the basic idea is that if you start running into problems, you're not going to have to dig in to try to find them. You're going to be able to, RavenDB will tell you about them directly. And for example, let's force RavenDB to do something slow. By the way, that's what I'm going to do now is, again, something that you cannot do in Mongo. So what this is doing right now is for each document in orders, generate another 100 documents that are replicas of it. Let me generate another one like that. You know, this is the live instance, the public instance. I'm running 2 of them at the same time. And now I'm going to go here. And imagine that I have no idea what's going on. And I'm worried. Hey, my CPU spiked. What's going on? Leaving aside that I can see that I have a lot of writes here. I don't know what's going on. Let's try to figure out. So I'm going here. And I can see, oh, this is taking a lot of CPU. What is it doing? So try to remember, I'm running an actual cloud system, which is a production environment. And this is now telling me this is the thread that is taking the time. It's going to be, and it's going to run, and here is the exact stack trace that is currently executing. So I can see, oh, I can see that you're putting a document. And I can see this coming from a patch operation. So I don't need to guess. I don't need to worry. It's there. It's applicable to me. When I'm talking about the biggest advantage that RavenDB has over any other database, that's the thing that I would say. There are a lot of other details around that. How we manage high availability, what sort of things we take ownership on, and what things we expect you to take ownership on. But all of them falls into the same category that RavenDB is going to make your life simpler, because we very explicitly design it to be this way.
There is one question which will also come. For this company, it's not that important, the price, you know. So but it will be asked as well. Comparing with Mongo Atlas, what would be the cost of
Roughly the same?
Cloud, RavenDB Cloud?
I would expect in terms of, if you compare hardware resources, you will find that we are roughly in the same pricing. If you compare, where was that? Give me a second. I want to find something. If you compare actual dollar spent versus value gained, you're going to see something really interesting. This is from a few days ago, and they switch from Elastic, from DynamoDB, Elasticsearch, and OpenSearch to RavenDB. And here is the spend that they had.
Please share this screen of this link. Also.
Oh yeah, sure, I will do that. And look at the latency. 1 to 2 seconds to 180 milliseconds. and they're running at 1,000 queries per second with 20% utilization. So this is literally just went up just a few days ago, start of the week. And then you realize that what sort of impact this has on your entire organization. For example, let's go and look into this one. You can see that I have here I have some text. What happens if I want to search for Florida in here? So what I'm doing right now, I'm enabling full text search. So instead of having to, I'm throwing the data into Mongo as a system of record, and then I'm going to be ETLing the process out into Elasticsearch. Then I have to cobble together a solution and monitoring, all sorts of stuff like that. You run the query, and RavenDB just got it for the first time, and we're talking about 50 million records that we have here. And
I think this is something what can be maybe really an argument to this company.
Yeah. So it is
because you know that data from MongoDB we will move to the data lake. I mean, there are a lot of components into this data management, but yeah.
Well, sorry, I did the demo. I forgot that I disabled indexing on this database.
That's perfect.
It's fine. We get the results shortly.
I got it. I mean, you don't have
another aspect. Look at this notion. So in terms of moving
Kafka,
to data lake,
I use Kafka as well. So you have Kafka connector. Is it Kafka connector kind of?
Correct. Yes. So you can take data directly from RavenDB and throw that into Kafka. If you have scenarios that call for the outputs pattern,
so sync and you have sync and what is the other to read and to write data from Kafka.
So the implementation that we have here, this is to write to Kafka. The ability to read from Kafka is in the roadmap. We will have that in Q1 of 2023.
Okay.
Yes.
Okay, good. So here's what I'm gonna do. To the end of the year, nothing is gonna happen because I will work, but these guys will not be in office. So next on the mid or on January, I will be again in Brussels, and I will tell them there is interesting database which I saw and was presented. I will also say by CEO, if you agree, to spark that we can get good support, from that point of view. And what I would do as well, I will finish what I'm doing currently with the MongoDB. I mean, it will be there, but I will use this Helm chart. That is what I could do and deploy it on Kubernetes on Azure and show it. But I mean, you don't have to do it, but it would be nice if I can get some demo account on cloud, Raven Cloud, or whatever is name of that service.
We have a free version there, yes.
Yeah.
You can just go and create a free version.
Okay, good. And I will show it as well that it from, let's say, from feature point of view, which let's say to have comfortable work, there is nothing that that RavenDB is behind, but I will share with you on chat this one. They will also look in this, so I don't know how to can I fight with these arguments. I really like what I saw. It's really good. I will I cannot send the chat here, but I will send it on LinkedIn.
Yeah, send us on LinkedIn or send it to I'm putting my email in the chat. You can send it out directly.
Yeah. So you see this, you will see this comparison, and I will have to give some answers here because the rank is low. Document store is not that low, it's 18, but score, it's really very low. 4 compared with MongoDB 469. So I will have to have nice, let's say, POC to show that this is really makes sense, especially with this what you show, that it can replace some components we don't use Elasticsearch, but when it comes with this data pipeline, so data management for different things, especially to prepare it for machine learning, that this RavenDB can really simplify things. Yeah. Anyway, I will not. Thank you very much for your presentation. Stay in touch. Next year, I will let you know what happened. Yeah. So have a nice evening.
You too.
Happy New Year, Hanukkah, yeah, whatever you celebrate.
Yes. Thank you.
Yeah.
Okay. Goodbye. Goodbye, everyone.
Bye. Ciao, ciao.